So how many people have been using catalysis on a regular basis? Okay. And is it platinum group type catalysis or is it biotransformations? Platinum group? Neither. What are you using? What a novel concept. I'm sorry? Ruthenium platinum group. Zeolites. Okay, so we'll have some fun with this. So some of you are very familiar with catalysts. We'll talk about some general catalysts, all the ones that you've named. We'll talk about biocatalysts and why we want to use them. So catalytic reagents are as selective as possible, are superior to stoichiometric reagents. This is a principle that was written by somebody who does a lot of synthetic chemistry. It was not written from somebody who does life cycle assessment. And it's not written by somebody who understands about the sustainability of key elements. And for many years, I had a huge amount of frustration because everybody would go in and talk about very interesting elements like indium and osmium. They would talk about platinum group, and they do to this day quite a bit, to the point of using iridium. And I alluded to it earlier on. Iridium only comes to the Earth by way of meteorites. All right? So yes, we were resupplied over Russia recently with a little bit of iridium. However, iridium is usually associated with the kind of impact that you find in the KT extinction. All right, to say that iridium is rare is an understatement. And yet, chemists are enthralled with platinum group type metals. If you look at the environmental cost associated with getting these metals, again, I personally believe it's irresponsible to use them. So hopefully, be able to define what a catalyst is and understand the importance as a green objective. And hopefully we'll talk about good catalysts versus catalysts that we need to get away from. So you all know what a catalyst is. It basically lowers the activation energy, and it doesn't get consumed in a reaction. So we like catalysts. It's a good idea. We struggle with finding a catalyst that lasts. So they lower the activation energy by forming bonds, by bringing the reactants together. This is really how biotransformation takes place, is bringing those reactions and holding them in a particular conformation, and then the reaction can take place. And that's really the value. It's an entropic change. Again, not a thermodynamic, it's a thermodynamics, different part of the equation, right? So it's important. Turnover factor, turnover number, is something that if you're doing catalysis work is something that you chase, right? How many turnovers can I get with this particular catalyst before it gets depleted? And I have to do something, either throw it out or regenerate the catalyst if I can, if it isn't poisoned. But this is a hugely important aspect. The other thing that's important from a green perspective is this heterogeneous as opposed to homogeneous catalysts. And we'll talk a little bit more about why that's so important. Catalyst selectivity, again, is why we like catalysts. And again, enzymes are far better in terms of their selectivity than most metal catalysts. So another reason that we should try and go towards enzymatic approaches. Few industrial catalysts achieve that level of selectivity that you will find routinely in an enzyme. So catalyst stability is hugely important. Yes, in the petrochemical industry, they can run catalysts sometimes for years, and that's good. A lot of these things are cobalt or cerium type catalysts. They're pretty robust by design over many years. In some cases, some of these catalysts have been worked on for 40 and 50 years. all right? Those are not the kinds of catalysts that most people use in the batch chemical operations. And the thing about most catalysts that you read in the literature is that their activity decays usually after about 5 cycles of running these things. They become inactive and they need to be disposed of. And yes, you can take palladium on carbon and you can recycle most of that, but from an industrial perspective, just losing 5% of that is millions of dollars. And I guarantee you that when you put it on a filter aid, you will lose about 5 to 10%. So again, getting away from platinum group catalysts is a good idea. This is just one example. Palladium complex used, high turnover, 100% atom efficiency, great example of an industrial benchmarking process used commercially every day. Homogeneous catalysts, again, we mix it up. We like homogeneous catalysts because we get very intimate contact with the reactants. The bad side is we throw it away, right? You typically cannot reclaim the homogeneous catalyst. The other is heterogeneous. From a green sustainability perspective, there's lots of strategies to try and heterogenize homogeneous catalysts, but many times we lose the activity of the catalyst. So ideally, we would always move towards heterogeneous catalysis in one way or another. Makes sense. So advantages, again, intimate contact for the homogeneous catalyst. It's quicker and simpler. And this is something that you will run into over and over again. You know, I said it about our use of petroleum. Petroleum is easy. It's there. It's cheap. Homogeneous catalyst, it's there. It's comparatively cheap. In an early R&D phase, we can use it. But you can't get past that point and into industrial scale using homogeneous catalysis unless it's a base metal catalyst like iron. If you got an iron catalyst, then you probably could afford to throw it away. Or enzymes is another one, because you can make enzymes renewably. So heterogeneous, there's the advantage. The disadvantage is this concentration of catalysts. So there's a lot of games, you know, those of you working with catalysts, of coming up with active sites on the bound catalyst. The type of site that promotes a given reaction, and then the side reactions. So again, it's a very difficult balance that they play. So examples that some of the people said they were working in, we heard about zeolites. No one mentioned titanium dioxide, but that's used quite a bit. Silica, aluminum, these are just ways in which we can support catalysts. And virtually all of these are being worked on to one extent or another. Someone mentioned that they're working on zeolites, and I'm sure they'd come up here and talk for hours on how good zeolites are and how useful they are. They're used extensively from an industrial perspective, and lots of people working on them for, you know, good reasons. There are chiral organometallic catalysts that are there. So we typically, metals, semiconducting, insulating, and acids, the function is there, and these are the examples. Again, most of these, iron and nickel, are fine. They're very abundant in the Earth's crust. These elements are not. Zinc has issues, 5 to 50 year supply. Most of these are Earth abundant right now. So again, from a standpoint of if I have to choose, and I want to choose something that's both green and more sustainable, then I want to go into something like an iron, a nickel, a cobalt, something like that. And oh, by the way, they're usually less toxic. It's interesting, nobody talks about the toxicity of these particular elements like platinum, silver, ruthenium. That's because the studies haven't been done, but those that have been done, and anyone who's worked with nano silver or nano gold knows how toxic they are to environmental organisms. Another one, I don't know, has anyone ever used phase transfer catalysis? So good, a couple people. So that is the idea where you're basically coupling the molecule and taking it into another phase where it reacts, where it normally wouldn't, just distribute into that phase so that you take it into that phase and react it, and then the product is produced. These are extremely useful for certain kinds of chemistries, particularly ones that have anionic or cationic functionality to them. And it makes them soluble in water where they would not be normally. Shuttling it back and forth from aqueous into the organic. That's what they do. Biocatalysis. So this is an area, again, that is up and coming. It has got a lot of attention in recent years, last 10 years in particular. And as synthetic biology has increased, so has biocatalysis. It's an extremely important tool. And again, I would hope that more chemists exploit enzymes in their design. Industrially, companies have gotten very good at coming up with a enzyme which has a certain functionality, and then expressing that functionality to a greater extent and industrializing the organism to produce the biocatalyst. This used to take 18 months and millions of dollars. It's now down to a cycle about 6 months and under $1 million. And it all has to do with the development of the technology to do that. This is another thing that's still very important, is whether you do a whole cell biocatalytic reaction or something that is an isolated enzyme. And there are advantages and disadvantages to doing those either way. Whole cells, higher activities, easier workup, purification of products. You can see the cons. So again, any approach that you take always has trade-offs. And the thing that you need to do is to just try one or the other. So again, what they do, as I mentioned, they find the parental gene, they get a hit, it makes it work, they end up with random mutations, they build up mutant libraries, all right, where the enzyme is expressed. They use the transformation there, they end up with, over here, lots of different variants, and then basically they analyze those and come down with a particular variant that has the highest transformation to do what they want to do. And again, that process, very stylized, but it happens very quickly nowadays. And I'm sure you're all familiar with how it's pretty much a lock and key type mechanism, where if it doesn't fit, it won't work. So the problem with biocatalysis is that they're very fragile, and pH is extremely important. This is true of any kind of fermentation process, and a lot of effort is spent in coming up with appropriate pH control. The second thing is temperature. And again, for any kind of living organism, you're extremely limited in that temperature range at which these work, unless, of course, you're dealing with thermophilic type organisms that operate at higher temperatures or organisms that work at lower temperatures. So again, pH and temperature will change the shape, and in a lock and key mechanism, if you don't have the right shape, you don't get the reaction taking place. So some advantages of biocatalysis: mild reaction conditions. Again, remember the first principle, room temperature and pressure, highly stereos and regio and chemoselective, variety of chemistries and substrates. And you'll notice that I put a question mark about environmentally friendly. Any ideas why I did that? That could be. We could end up with something that we don't know what we're dealing with. So that's closer to where I was going with this, is that it gets back to how we create enzymes. This is a fermentation process. So we have large amounts of water. We use a large number of salts like potassium, phosphorus, and magnesium type salts. We do intimate pH control, typically with ammonia. Large volumes of water which we heat. We give off a large amount of CO2 in the form of expired CO2 from the organism. So the notion that these are environmentally friendly is, again, once again, trading impacts. All right? Where in the life cycle are you going to trade your impact? So everything has an impact, everything has a cost, but once again, look at the whole system and try and understand where you can optimize the system to have the fewest impacts. So the problem with biocatalysis is really trying to find enough targets. And what you will find commercially is that people have large libraries, and it's really hit and miss. So all of the effort has been to find large libraries and then go through high throughput screening. Once again, academically, that's very difficult to do, but industrially, that's what's done. Molecular biology, as I mentioned many times, is something that's really changing the face of how biocatalysis is done, and it's making it much more accessible on a routine basis. So again, I'm very optimistic about where biocatalysis is going to go in the future. These are the kinds of reactions that you will find most often, okay? The oxidations and reductions, the hydrolysis type reactions, O and N demethylations. And these typically are done chirally as well. So that's the other advantage that we have with these kinds of reactions. So again, why are they considered green? Ambient temperature and pressure, aqueous solvents. Everyone likes water. Benign reagents, there's not heavy metals, there's not platinum group metals, there's not other strong acids or bases. Long history of safe use, and the stereoselectivity. Many times you can reduce the number of steps. Rich talked about Lipitor. He didn't talk about another molecule, progobalin, which Pfizer did. 3 enzymatic steps to replace something that was about 7 or 8 steps. So once again, it really offers an opportunity to change the way in which chemistry is done altogether. So these are the kinds of advantages that we get with catalysts in general. Increase yield, reduce cycle time, consolidate unit operation, volume efficiencies. Quality is usually better. Environmental performance, again, solvent reduction or replacement. You are very specific, very chemoselective. Alternate raw materials. This one about exotherms is an important one because that's something that, from a process safety standpoint, we'll talk a little bit more in the last lecture on inherent safety, but it's extremely important. So these are some of the kinds of reactions that we typically like to go after. And again, you'll notice that all of these are largely directed at what? Feedstock. Petroleum feedstocks. Alkane activation, selective oxidation of the carbon-carbon or carbon double bond, alkylations, olefin polymerizations. These are all petrochemical, right? We've got to transition away from petroleum and into doing these kinds of reactions, catalytic reactions, with natural products. Why can't we cleave proteins and get at all of that chemical diversity by using enzymes? These are the bugaboos for catalysts. The turnover number, as I mentioned many times, is the big problem, is getting a high enough turnover number. Precious metals, we've talked about. The fact that it's oftentimes very difficult to produce a heterogeneous catalyst. Again, These are some of the barriers from an industrial standpoint. Catalysts right off the shelf. If we could get catalysts off the shelf and do it, we would not have had a history of close to 100 years of catalyst development, and it's still going strong. I don't know when we'll exhaust catalyst development. It's going to be something that chemists always do. Most chemists don't know as much about catalysts as they ought to, so they don't think about how they can be used, and this notion of recyclability is rarely thought about. Again, it's usually just we use it for one thing, we demonstrate a reaction that no one's ever demonstrated, and then we pitch the catalyst, unless it's a platinum group, and then we might recycle it. Lots of known reactions. So this is something that academics like to do. They like to demonstrate a new catalyst with an existing reaction. Why don't we have a different kind of reaction using a new catalyst? I don't understand that, but that is what it is. That's your challenge. Change that particular dynamic. We have lots of named reactions. We need to come up with lots of new reactions that do things at a much more efficient way. Lots of work needs to be done in terms of reaction engineering, which again is not done sufficiently today. So as I mentioned, catalysts have been an active area of research and development for a long, long time because chemically they're so useful to us. It's a major part. No matter what green chemistry symposium you go to, you will typically find lots of catalyst work. Not all catalysts are green from the life cycle. And think about biocatalysis and base metal. That is iron, nickel, things like that, aluminum. There's lots of those materials. There's not a lot of most of the materials that you use for most catalytic reactions. And with that, I need to stop. And we need to get into the exercise, which is pick a catalyst, any catalyst.